see the screen?
Mm-hmm.
Okay. So welcome everybody. I just joined. I just finished another lecture. Yeah, so the idea for today was to, yesterday I gave mostly an overview, very qualitative, on numerical relativity and where numerical relativity can be helpful and what are the typical problems that are treated in numerical relativity. So today I want to do something a bit more basic, so explain better some of the things that yesterday I just mentioned, and you know, show actually some equation and so on. So the presentation will be, of course, on this whiteboard, and it will be basic. So maybe some of you are already expert. I mean, many of you that are not involved in numerical relativity work are in any case expert with 3+1 geometry and initial value formulation of general relativity, because it is in general useful for many other things. Once for just to mention one, the Hamiltonian formulation of GR. But still, I think it is useful if I go through some of the key ideas. And of course, if you know already these things, you might not need to follow, to attend. But for those that don't know, or that they have very superficial things, that they might still find it interesting. And so I want to try to cover three basic topics, or sketch. It's not really a full treatment, but at least sketch three basic topics. One is some geometry, 3+1 geometry. So how do we divide space-time and space and time? The second part, that means that deals with general relativity, is really how do we formulate Einstein equation into this 3+1 geometry. And see this go often under the name of ADM formalism, but as Thibault yesterday told me correctly, it's actually a contribution of many other people, French mathematician and even York. That's why I added him in this in this title, because in particular the notation that I will follow, the variable that I will use, are ultimately due to him. And finally, in the last part, I want to talk a bit about the Cauchy problem. So how do we treat, how do we set up a well-posed initial value problem in general relativity? What's the step between, you know, point 2 and an actual formulation that are used in numerical relativity? And again, here will be very sketchy as well. So in this page, I summarized the notation. I don't think I have to comment much about that. The thing that you might need to remember is that IJK are spatial indexes, and that often to separate, you know, quantity defined in 4D on the 4-dimensional space-time, I will put this 4 here on the top left, because there will be also quantity that are defined only on certain hypersurfaces, so submanifold of that. And yeah, the disclaimer here is that the discussion is inevitably simplified. It's more to give you an idea and a flavor of that, or to recap in case you know it. So let me start. What we start from is from our space-time, which is 4-dimensional, at least here. And in the space-time, what we have or what we can think of is this manifold that we call it M. And this is equipped with the metric. So there will be also covariant derivative that I will call this way. And associated to that, of course, there will be this 4-dimensional Riemann tensor that I will define this way. So on this space-time, in order to start to talk about, say, evolution problem or Cauchy problem, on this space-time, what one does is to introduce a foliation. Which essentially boils down to introduce a scalar field, which I will call T, and then later I will take it as one of the coordinates, such that the gradient of this, or better, the vector associated to the gradient of that is time-like everywhere. And so I have everywhere a time-like, a time direction, okay? And of course, the norm, this vector here defines spatial hypersurfaces, which are 3D, and are usually indicated as sigma t. And they are identified by their normal vector, which I would call n, which I take a normalization constant times this dta. So this is called normal vector. And this normalization constant play an important role, as we will see. And it's called the lapse function. So it's something that we already introduced yesterday, and we will see better today its meaning. The name already says what it is. So this notation in particular was introduced by Wheeler, but the lapse function itself was not. It was already there before in other notation, maybe with other names. So going back to the thing, what this procedure gives you, as the name says, is a foliation, so kind of subdivision of the manifold into many of these hypersurfaces, each of which is parameterized by a value of t, so we'll call it sigma t, which is submanifold of M. And they are equipped, of course, with the metric and with the covariant derivative there. And of course, they have also their own, there is also the Riemann tensor there associated to this gamma and covariant derivative. And so the metric it's called tree metric. It is essentially the metric induced with the pullback operation. And in some coordinate, you can think of it as given by a sort of expression like that. And if you do the calculation here, what you find is that this is Gij plus NaAj. So from this metric, as I mentioned before, you get a three-covariant derivative, which I indicate like D, and of course the Riemann tensor in 3D. Okay, so this defines, in some sense, the intrinsic geometry of these hypersurfaces here. And as we mentioned yesterday, there's something else. So there is another curvature. that essentially tells how these sigma bend into M. Okay. So in general, you might define it in different ways, but one way of defining is just the projection of the derivative of the normal vector. So you take your normal vector, and then you contract it twice with the with this object here, which is the metric with index raises, but it is effectively the projector into these hypersurfaces. So this measures the change of n, or better, the trace of this object. Measure the trace of measure the change of n, of the vector n, when it is transported along sigma. And so gives you an idea of how this curves. And so this is called the extrinsic curvature. Of course, opposed to the intrinsic, which would be given by the Relativity Riemann tensor. So one can show that another way of an equivalent way of writing this equation, or if you want to define, the extrinsic curvature, up to you, is this. Where L is the lead derivative along M, and M is a vector that is proportional to n, to the normal vector, and a square is simply minus alpha square. So this is an important equation, the first important equation that we have already seen yesterday, and I mentioned this yesterday, so let's give it a name. Oops, page. So equation 1, you can see it as a kinematical sort of relation. That essentially connects the time derivative of the metric to its velocity, which is k. Okay, there's someone. See, a bit more technically, the vector m is the vector that carries point from sigma t to the next. Say sigma plus delta t, from one surface to another. And this lead derivative here that defines that is in equation 1, analogously, is the quantity that transports tensors in general from sigma t to sigma plus t plus delta t. So another way of saying this is that these hypersurfaces sigma are identified by the diffeomorphism that is generated by M. And yet another way of considering this equation, you can see that, or you can Our intuition can suggest that the 4D manifold can be viewed in the sense as the time development of this sigma hypersurfaces. So we have talked about before the meaning of lapse and so on. So in order to get a better grasp on this formulas, let's look into detail into my first point here. So take one point here in sigma t, and let's consider the next hypersurface, sigma t plus delta t. What this m vector does is to push the point P into the next that we will call P prime. And so the value of the scalar function of this T of P prime, it's simply given by T plus a delta T times the vector M, and by the definition of gradient, this is Tp plus delta T Ma dTA. And you can substitute here the definition of M, and you obtain Tp plus delta T, plus delta T, because the square of n is -1, and dt is minus alpha. Let's see if I did it before. Did I give it? Yeah, sorry, there's a minus sign here. No, sorry, not here. There's a minus sign here, correct. Yeah. So the simple calculation proves that this m vector is the one that sends point from sigma to P1, and analogously you can argue about point 2. But this essentially gives you the meaning of this lapse function. So if you calculate the observer that are associated with n or m are called the Eulerian observer. And if you calculate the proper time of this Eulerian observer, what you find is simply the lapse. So you see that this lapse function, as the name suggests, really controls how the proper time of how the time of Eulerian observer evolves, and in particular, if you take the lapse identically equal to 1, the t coordinate that you are using is precisely the proper time of this observer. So this was this should complete the discussion of yesterday when we had this experiment in which we virtually evolve the Einstein equation using lapse identically equal to 1, and we finished against the Schwarzschild singularity in a finite time. Okay. So to give you also an example, I think I discussed it also yesterday, but to give you an example, instead of the meaning of the extrinsic curvature, what you can consider is R3 as a manifold, and consider shapes into this manifold. So the simplest thing that we can imagine is R2. Okay, and so in this case we know that both the two, in this case the two-dimensional Riemann of this is 0, and also the two-dimensional extrinsic curvature is 0. If you now take a cylinder, so C2, say of radius A, then you can unfold the cylinder, you can cut it somewhere and open it, and this suggests that also in this case the intrinsic curvature of this cylinder is 0. Okay. But if you do this exercise and calculate the extrinsic curvature of that, and you use cylindrical coordinate, you find that this component k phi is minus a, okay, and the trace of k is minus 1a. So this is a case in which you see clearly the difference between these two definitions. And of course, the third example would be the sphere, again of radius a. Well, you can do the exercise here. You find obviously that R I, J, K, A, it's different from 0, and K as well. But they have different values, and in particular, the trace of K is minus 2A over A. Okay, so this should give an idea about the extrinsic curvature for those that have never heard about that. Now, the next things that one does is to introduce coordinate. And well, on the entire manifold. And one obvious choice for adapted coordinate is to take this t and some coordinate on the spatial hypersurface sigma. And this essentially gives you basis for the tangent space, which is dt and di. Whereas the dt is usually called the time vector. Let me draw something else. So we have seen before that the m or n vector send point from P to P prime. Here now you have to imagine that you have some coordinate here, xi, and in this picture, the time vector dt is a vector that is tangent to this coordinate lines of constant coordinate here on sigma t. Okay, in general, this vector. Let me see. So this is m, and this is dt. So in general, this vector is not the same as m. It shares some properties, like transporting the points, but is not parallel. Okay. And so in general, T is tangent to lines of coordinate, which means that here, what color is this? Which means here the point Q as this, the xi here have the same value as there, as below. Okay, so it's the same constant here. The three constants that are here are the same as here. But as I said before, this vector in general is not the same as M. Okay, so analogously through M, drags T, sigma T, but it is a different one. So dt in general writes like A plus B, where this beta is called shift vector, and it's a spatial vector. So in this picture here, this beta is the vector that connects P prime to Q. Okay, and this means that the coordinate of P prime is something like xi minus beta I dt. So this tells you that in general, this dt vector is not time-like. If you take its norm, let's write it this way. It is not perfect, but you find that this is minus alpha square plus beta square. So its character depends on the choice of beta. And obviously, what the shift vector does, is to control the coordinate. When they go from sigma t to sigma t plus delta t. Okay, so as we will see, also as we discussed yesterday as well, alpha and beta, so the Laplace and shift vector, are not prescribed by general relativity, and they just when we do now the 3+1 decomposition, they are just four quantity that reflects the gauge freedom. In this 3+1 decomposition. So at this point, you can write the metric. You'd have to do some calculation, but those are not particularly complicated. And this coordinate, the metric writes in this way. Which perhaps highlight also some, again, the meaning. So this is what is sometimes called the metric written in terms of 3D or spatial or 3+1 quantities. And to give you an example, you can write you can write the weak field metric. in this form. So you all know that the metric is usually written this way. Where F is the flat metric, Minkowski, and where phi here is the Newtonian potential. So you can simply read off what are this quantity you can simply read off what are the quantity above here. Let's call this equation G. In this case of the weak field metric, and you see that the lapse is this term here, square root. And if you expand it, it's 1 plus the Newtonian potential. So I think yesterday when I showed a movie of some binary black hole simulation, there was some color plot of the lapse, and I mentioned this is basically what can be interpreted as the Newtonian potential. That's what I was thinking about. In this case, the shift is 0, and the trimetric is a conformal factor given again by this Newtonian potential times the flat metric. Perhaps a more interesting example is this Schwarzschild metric. And let's take, because it's easy to identify things, let's take isotropic coordinate. In this case, G is 1 minus m over 2r squared. There's a quantity or function called psi to the minus 2 that I'm going to define. The same quantity to the 4th power tr squared plus r squared omega squared. And this quantity here, psi, is defined as a similar function, but with plus. So this is the conformal factor of Schwarzschild in isotropic coordinate. And again, as above, you can simply look at this metric and compare to G, to the 3 plus 1 form, and you immediately identify a lapse as this object here. Shift is 0 again, and gamma ij is again this conformal factor, which is now as a different function, fij, and you can also calculate the extrinsic curvature, and obviously you find 0. There's a relation between this metric and, as you know, there's a relation between this metric and the weak field metric. So if you take psi, if you compare, you see that psi is 2 for power, which again indicated we are always talking about this conformal factor, which can be identified as the Newton potential in some sense. So this is the weak field limit of Schwarzschild. Last example, and then I think you are sufficiently confident with that. Let's take G, the generic metric in 3 plus 1 form, and we choose lapse equal 1 and shift equals 0. And of course, you find that G is minus dt squared plus dj. And you see that in this case, t, the coordinate, the adapted coordinate of this Eulerian observer is the proper time, as we already argued before. This gauge here is what we analyzed in our virtual experiment yesterday, and it's called geodesic gauge. It has also other name. This is one of the names. And if you choose this gauge, say in your numerical relativity simulation, the coordinate that you are using in your simulation are basically following geodesics. This was the message of yesterday. So what we have seen yesterday is that black hole evolution, say Schwarzschild black hole evolution in this gauge, gave a code crash at tau, which in this case is equal to the t, which is 2 pi, which is the time, proper time that an observer on 2n needs to arrive employs to arrive to the singularity. Okay, so this was a short overview on the 3+1. Let me go to general relativity. So everything that has been done so far is of course independent on Einstein equation. And the next obvious step is to say, okay, now we have some identifier structure, how to divide space-time into space and time. So let's try to see how Einstein theory look, or Einstein equation look into this formalism, and what we will arrive is this equation that we now called ADM plus York equation. So what is the starting point here? Well, we simply want to rewrite Einstein equation in 3+1 form, which basically means substituting G as, say, fundamental variable with the set of gamma, the trimetric, alpha, and beta, and the 4 Riemann with the set of the 3 Riemann, the extrinsic curvature, and the covariant derivative on the 3 hypersurfaces. So this can be done using identities, which of course I'm not discussing here. They are called Gauss, Codazzi, Ricci identities. They are geometrical identities, and they precisely relate, metric and Riemann of an ambient metric of an ambient manifold, if you want, to the one in the embedding. So if you want to do it by hand, go ahead. The result, they're not very complicated, but let's skip this. The result in vacuum for simplicity looks something like that. 0 equal the Ricci scalar plus the extrinsic curvature trace square minus this contraction. 0 equal the divergence of this quantity, mixed indexes, minus the k. Again, k is the trace of the extrinsic curvature. And then you have Lie derivative along M of gamma ij, Lie derivative of kappa ij equal to alpha kij. And Lie derivative along M of k, the extrinsic curvature is the ij. This is a bit longer equation. Okay, kappa j. Okay. So this is the form of, this is fully equivalent to the Einstein equation, but written in these variables. Okay. And this one, the third equation, we have already found. Is it here? It's simply the definition of the extrinsic curvature. Okay. So it's a purely geometrical kinematical equation, and so let's call it K. I will call this D for a reason that will be clear. And this is one possible form of what we could call ADMY equations. So some observations. So these are equivalent to our starting point. We just have redefined variable in some sense. So in particular, covariance, the coordinate invariance is maintained, and here you don't see any equation for lapse and shift because there are none. Okay, you have to you have four equations to specify, which in some sense corresponds to your initial gauge freedom, and you still have it here. It's just encoded in this. It's just encoded into this function. So if you want to solve this equation, you need to specify them, which means to prescribe. For instance, you can use a geodesic gauge, or define or invent or define the equation for those. However, in some sense, it's helpful to rewrite the equation in this way, because you can think, because now we can formulate the Cauchy problem in the sense that what we want to think of, or what we should think of, is that of this Lie derivative in n direction as a time derivative. And so you see that some of these equations have the structure of time derivative of a fundamental variable equals its velocity, time derivative of the velocity equals something that, of course, we are going to naively identify with the acceleration or with the dynamical part. And so the idea here is to ask, okay, what kind of equation are those? And the simple answer, which is a bit naive, but I think it's okay for today, is that you can think of sort of mixed hyperbolic for those equations that contain time derivative, and elliptic equation that do not contain this time derivative, and in fact they should be called constraint. For what variable? Well, for the basic variable, just a second. Alessandro tells me that I can have 5 minutes of break, but let me finish this. So you can think of evolution plus constraint equation for what variable? Well, for what we said before. The metric, the extrinsic curvature, and alpha and beta I, where only these, of course, are specified, and this needs to be prescribed algebraically or with equations. Yeah, no, I want to continue and continue here. So let's look a bit more in detail about these equations. So let's look at the very first. But this is an equation that I will call this right-hand side C0. So I'll write the equation C0 equals 0. And we can call it H. This I will write Ci and I will call it M. So what is it here? The equation C0 equals 0, or what I called H, it's a scalar equation that involves gamma plus spatial derivative, first and second order derivative, and K. H U. So if you look at it in detail, well, you find out that this is a nonlinear equation, and you can call it elliptic type or elliptic-like. In particular, there's no time derivative. Where again, by time, I mean this the derivative along M. And most importantly, this is defined or involves quantity that are defined on a single hypersurface in 3D. So as you expect from the name, this is a constraint and it's called the Hamiltonian constraint. Next, we have the M equation, which we wrote Ci equals 0. So this is one rank 1 tensor equation. So 3 equations involving Kij plus spatial again, first derivative. It's also nonlinear. And you can also consider it as an elliptic-like equation. So the real classification of this equation can be complicated. And it's not straightforward from, at this point, but you can consider it that way. Most importantly, this is also defined on this hypersurfaces. So this is also constrained, and this go under the name of momentum constraint. And then we have the others. The others instead are evolution equations, K and D. So K is one rank 2 equation for the symmetric tensor gamma ij. So this is 6 equations involving, in this case, first time derivative, again in the sense of the derivative along M, and involving Kij, the velocity. So this is what one could define the kinematical, at least for today, the kinematical equation. And finally, we have the D equation, which is a similar one. And we consider it an equation for Kij, and involves also first time derivative of Kij plus second partial derivatives of the metric, of the trimetric. Okay, and this is what we can define to be a dynamical equation. Okay, so in some sense, this is what really defines the time evolution given by general relativity. So there's an interesting note that I don't have the time to develop, but if you suitably massage this equation, in particular, if you do conformal decomposition of the metric, so you write it psi for gamma tilde, and you try the right equation for this conformal factor and conformal metric, the weak field limit of the dynamical equations turns out to be the Poisson equation. Okay, where we have seen before that psi is related to 1 minus the gravitation, 1 minus 1 out the gravitational potential. Okay, so the structure is clear now, or should be sufficiently clear. This equation above in some sense separate from in two constraint equation, so what we call what we could call C A or C mu equal 0, and these are the constraints, and they are defined on a sigma t, on a single hypersurface, and the evolution equation which schematically have this form. And they govern they govern the time evolution of the problem. So from sigma t to sigma t plus delta t. So I'm not sure if you are familiar with this. Perhaps not exactly this, but you're certainly familiar with the Maxwell equation. So the structures here is completely analogous to Maxwell equation. Especially if you take as a fundamental variable the vector potential. So in this case, what you have is a constraint that look like that. And the time evolution, this is t. And the time evolution of this constraint is zero, it's identically zero. And you have instead wave-like equations that can be written like that in Lorentz gauge. So the structure is identical, conceptually at least. There are many differences, but you still have these two blocks. And so this is a helpful example because what we know from Maxwell theory is that this constraint here is transported along the dynamics, which is a way to say that if C is equal to 0 at t equals 0, then C is equal to 0 for all the other times. And this is interesting because in some sense, if you now go back to the numerical relativity perspective, suggests you that you could set up free evolution schemes, called free evolution schemes, in which you solve, they are called like that in numerical relativity at least, in which you solve the constraint only at the initial hypersurface, and then you solve only the dynamical equation in the other t at the other times, but you don't need to solve the constraint all the time step. And so a natural question here is to say, okay, what happens in GR and the short answer is that it happens the same. So in other terms, in general relativity, if your constraints are solved on some sigma 0, then they will be solved also at future times. And there's the proof is not complicated. There are many proofs of that. I want to discuss one proof of this, or at least sketch it. because it will be helpful for the last part. It's the simplest I know. Maybe there are others. So the idea here is to consider an extended theory. We could write down the Lagrangian and so on, but let's just work at the equation of motion level. And this is called a Z4 system of equation, and writes this way. So it's an extended theory, where the Z is a new vector field. Of course, if you have this Z that is identically 0, this would be an algebraic constraint now. Then you recover general relativity automatically. Okay. And of course, you can perform the 3+1 decomposition of this system as well. The result again, schematically, it's very similar to the previous. You have time evolution for gamma, you have time evolution for k. This is a scheme. I will skip all the indexes. The time evolution for k is as the previous one, plus the sum derivative of spatial derivative of the z vector. And here, instead of having the constraint in this case, you have additional evolution equation, one of which is essentially proportional to the Hamiltonian constraint, and the other that is essentially proportional to the momentum constraint. So in some sense, with this extension, all the equation becomes dynamical. And if you consider the Bianchi identity, they give you an equation for Z that turns out to be linear. So this means that this equation here implies that if at t equals 0, you have a solution of the Einstein constraint, and you have your okay, that's not very nice to write, but if at t equals 0, you have all the constraints satisfied, and you have a solution of general relativity, so Z is equal to 0, and also its time derivative. Then the Z4 system remain general relativity for all the time, which means that constraints are satisfied all the time. So this is a simple way to get the fact that constraints are transported even in this in this approach. And so to summarize this part, the way to tackle 3+1 general relativity, at least from a conceptual point of view, could be first to solve an initial data problem in which one solves the constraint and define your initial hypersurfaces, and afterward to start from this sigma 0 with the free evolution that solves k and d for sigma t larger than 0. So there are other possibilities which I don't discuss here, but this is currently the way that, say, binary black hole simulation are done. And of course, in this case, what you have to solve here, it's a Cauchy initial value problem. I don't know how much time I have. I want to mention something else. And
Sebastiano,
yeah,
we have still 20 minutes, more or less.
Yeah, so I have the third part, but before that, I wanted to. So let me go ahead. I wanted to mention that this is an approach that many of you already probably know, to go for a Hamiltonian formulation of general relativity. So let me mention this. For some of you, this will be just notation, maybe other, I don't know. So there one can approach basically the problem by defining an action this way, plus some boundary term, but, which in our notation would be written this way. And so you see that what this Hamiltonian constraint does is to play the role of Lagrangian density. And from this, which we call L, from this you define an Hamiltonian, well, you define conjugate momenta. And then you can define an Hamiltonian in the usual way. And again, in this notation, this turns out to be something like that. And so I think this is interesting because, first of all, well, this conjugate momenta Pij are simply another variable for the extrinsic curvature. So they are not the same thing. And that's the difference between the ADM paper and the York choice. But also you see again that this lapse and shift becomes Lagrangian multiplier here that enforce the constraint. So this what would be the short summary of the formulation in this notation place that I presented. I just have a couple of 4 pages. I don't know if I should go ahead or continue or make a break. I don't have much more to say.
I think that you should continue, and then we stop earlier, and then we take a break at the end, or taking time for questions. So
Okay.
go ahead.
So let's now do the third part. I don't want to deal with the initial data problem. In my opinion, this is more complicated than the evolution problem. As also we discussed a bit yesterday. There are complicated elliptic-like equations coupled, nonlinear, for which well-posedness is not always known, so one has to make ad hoc choices. Whereas we have more results, I would say, about the evolution problem. That's why I'm talking about that. And here, the thing to remember is that if you want, well, you want to know in general if Cauchy problem is well posed. But especially if you want to set up numerical methods to solve complicated equations, you first of all want to know that certainly what you're using is well posed. Okay, so what is well posedness? Well, again, you might know this, but this is the simplest definition that I know. Problem is well posed. A PDE problem is well posed if there's a solution, it's unique, and if it depends continuously on whatever boundary data you give, at least locally. Well, sorry. And this holds for any PDE problem. It's a good definition, that more or less holds for any PDE problem. So you have existence, uniqueness, and discontinuous dependence. So for hyperbolic problem, that's the type of evolution that's the type of problem that we think about for an evolution. Right here. So hyperbolic means wave-like. Hyperbolic problems are those that describe propagation of physical quantity at finite speed. There are some more definitions, and there are some concepts can be better specified. And again, this is very simplified, but I want to mention it. So if you have second order PDE system, we call it strongly hyperbolic. If the principal part of the system is in the form of wave equation. So box U as any state vector, in principal part has to be equal to 0. And there's a theorem that says that this property of strong hyperbolicity implies well-posedness. of the Cauchy problem. So if you want to know if your Einstein system is in the sense of Cauchy problem is well posed, what you have to prove is strong hyperbolism, this special property, okay? And again, this definition 2 is simplified, but essentially what you want to see or what you want to look for is to a system that as a PDE form in principal part looks like wave equation. So the obvious question here would be, okay, is this system that we have just derived with this particular variable made of the kinematical, the dynamical, plus the gauge. You cannot disentangle the gauge here because you have to solve it together. Strongly hyperbolic. So if yes, you can go ahead and try to solve it numerically. And the answer is yes, but there is a but. So the but is that there are conditions, and the conditions are that the shift has to be prescribed. The lapse belongs to a certain class of equation proposed for the lapse. This is known as the Bona-Masso family. Okay, and the third is that the momentum constraint is identically satisfied during the evolution. So here the fact that the lapse belong to, so this class, this Bona-Masso family of gauge condition is actually good. So harmonic gauge belongs to this, and other gauges, punctual gauges belongs to this. This is good. But in practice, say 1 and 3, sorry, are too restrictive. Say for numerical purposes. The reason, for example, is that you want to prescribe the shift in such a way you minimize grid distortion, and you might want to specify some complicated equation there. And also numerically, the momentum constraint is never identically satisfied. So algorithmic error introduce a discretization, and algorithmic errors are there all the time. And this certainly violate condition 3. Well, it turns out to be this is not a route that we can pursue. So essentially what one has to do is need to find something else. And I want to present you how this problem has been solved. A very old solution, very well known, probably by all of you, and old but yet a bit more modern solution. So in the end, the message is that we don't have to throw away these ADM equations, but we can use them and we can modify them. But somehow the first proof of well-posedness came in imposing harmonic gauge. Long time ago. And to introduce this, let's just forget for a second about the 3+1 decomposition, and just look at the equation in vacuum, the 4D equation in vacuum. So in vacuum, we have the reach equals 0, and if you write it in terms of partial derivative, you have an expression of this type. Let me write simply Q alpha beta, and these are terms, these Q are terms that depend on the metric and on the first derivative, so they do not belong to the principal part. Whereas the first terms here, the first two terms, this contains the highest derivative, which is the definition of principal part. And simplifying a long story, in this expression, the quantity gamma, by definition, is this contraction. That if you calculate a bit here, it's a simple calculation, you find that they are simply these four functions. So what's the obvious thing to do? Let's remember the definition of, the simple definition of well-posedness. We want this equation to look box U equals 0 in principal part. Well, the obvious way to make it explicitly strongly, how's it called? To make it strongly hyperbolic is to simply impose harmonic gauge. So if you impose this gauge, you get box G in principal part. And you do have a Einstein system that is well posed. Okay, so this is a good starting point. So this is in fact what a generalization of a generalization of this harmonic gauge. So the generalized harmonic gauge is what, for example, Pretorio used, is what is implemented in some of the state-of-art codes. And so you can do black hole evolutions here using that. There's another nice observation that if you take, if you take your Z4 scheme that I've introduced before, and you set this vector equal to the Z vector equal to gamma alpha, well, this is equivalent to GR in harmonic gauge. So there's a tight connection between this extended system that that I've shown before and the harmonic gauge. Is this the only Is this the only formulation that is known to be well posed? Well, the answer is no. And in particular, and this is my very last part, in particular, you might ask a question and say, okay, in harmonic gauge, the gauge is fixed. Do formulation in which we have gauge flexibility exist? Do well posed formulation with gauge flexibility exist? This is a fair question because, as we discussed yesterday, our success in evolving black hole, for example, black hole space-time, really depends on the gauge. And in general, for any application, you might want to be free to specify a gauge that maintains the well-posedness, but is otherwise tailored to your particular problem. And the answer is yes. So this formulation nowadays that are mostly used, I would say, for gravitational waveform are these two, BSS and OK, that comes from the initial of group of people, three different groups that proposed it, and Z4C, which is a variant that is derived from the formulas that I've just presented above. And so I want to sketch you how you can obtain some of those, and the logic is precisely the same that has been, or very similar to the logic that we have used for the harmonic gauge, but with some differences. So in particular, if you consider at this point our ADM equations, you can combine the kinematical equation with the dynamical equation. So if you remember, these are first order in time equation for the two variable. So you can combine them to obtain a second order in time equation for gamma j. What you obtain, at least at the sketchy level, is something like that. A second derivative of gamma j, again, principal part is something like 2 alpha the Ricci tensor. And if you now develop this, I will not put all the quantities, but the structure of this right-hand side is essentially the Laplacian operator in the covariant derivative, plus other terms that look this way. Yeah, it's the same. So this is just a symmetry. Okay, plus other term. And again, if you look at this equation and think to our definition of well-posedness, you see that these are all second derivatives. So this is the principal part. Okay. You see that this is a good term, whereas this is the bad term. Essentially, what you do with harmonic gauge is to throw away this term here, which you can do also here, of course, just with another notation.
Eva,
yeah.
Your time is over.
I'm done.
Okay.
I just have one last thing. Yeah, with harmonic edge, you would throw away this and keep something like that. But without the bad term, we would have a manifestly strongly hyperbolic equation. And so we would be done. So instead of fixing the gauge, the idea here would be to introduce a new field. Say, let's call it Fk, which is precisely the derivative here. The divergence of the derivative of the trimetric in the bed term. So this one here and this one here. And find an equation for this, and find an evolution equation for this new field. This is, of course, the tricky part, but it's simple. Because if you take the time derivative, even partial, this is h. You can switch here this derivative. And you see that this is something in the form. This is a time derivative of the trimetric. So this is in the form of a spatial derivative of the extrinsic curvature. Okay. And so this is nothing else, something that must be proportional to the momentum constraint. So a natural way to obtain an evolution equation for f is to use the momentum constraint. Note that this was exactly the problematic aspect in the hyperbolicity statement of the ADM equation. Okay, so this actually proves to be a successful strategy. And is the starting point to derive this other formulation that I mentioned. So before concluding and summarizes, note that this equation here is very similar, if not the same, to the Z4 equation that look like that. So there's again a connection with that formulation and this approach of finding hyperbolic hyperbolic schemes. Okay, the way it proceeds to reach this BSSN OK and Z4C formulation is just to further consider a conformal decomposition of this of the fundamental variable. This is because it is advantages. It has some advantages in that case. So let me put the last note. Obtain with this idea, but the further conformal decomposition.
Okay. Look, because we are 5 minutes past, I suggest we stop.
Yeah.
For what was it, 10 minutes, and then maybe we can postpone the. I mean, if there are urgent questions, we can have them now, because the original idea was to have 10 minutes of question and then plenty of time for discussion. So maybe we can have one urgent question if it is now, and then we can have a break. So So I don't know if there are questions all around.